Yeah. Hey everybody. Tonight we'll be going over chapter 8. The PowerPoints I'm going to be going over are the short version of chapter 8. I have the long version there. I knew I needed the book with me for a reason. So there's some pages in chapter 8 you don't need to read. Okay, we're not going to worry with the logistic regression stuff. So I'm going to flip through and tell you which pages you don't need to worry about in the chapter. So if you look at page 291, where it says regression models with logarithms. You don't need to read that section all the way through to page 299. Okay, then you need to know everything else in the chapter. So basically, the bottom section of 291 all the way through 299, you don't need to read. Okay, so we'll get to that. I'm not a fan of logistic regression personally. Neither are most psychologists because it doesn't use real numbers. But economists love it. So, we'll get to that when we get to it. But I don't want to convolute things in this chapter. Just we'll stay focused on the gist of what's in the chapter, and then get to that stuff later. But I'm going to go ahead and share my screen now. All right. Can you guys see the PowerPoints? Okay. All right. And, all right. Okay, here we go. So we're going to be adding a few things to what we already have covered. So we did linear regression. That's probably what most of you guys are using in your project. You can take some of what we do today and put that into your projects if you want to. You're not required to by any stretch of the imagination, but you can take variables and multiply them together, which is pretty much what we're talking about today. Is looking at you have your columns of data. Well, that's what I wanted to show you. Here, let me get out of share and pull up the spreadsheet. Okay, so this is I don't know if you guys have probably not looked at it yet, but can you see my Excel file? Okay, so you see how this is the example problem I do in chapter 8. I already have those videos up, so we're just going to go over the PowerPoint tonight, but I put 2 videos on how to do what we're talking about tonight. So last week we just took, say, what we're trying to predict, our Y variable, applicants. And then we would use 2 columns of data, or in this example, 2 columns, to try to predict applicants. So these would be our X variables, marketing and employed, and applicants. But what we're doing today is we're saying, hey, maybe you can multiply these 2 things together. And what that does is creates an interaction effect. So we're saying that, yeah, maybe marketing independently affects the thing we're trying to predict, and maybe employed predicts applicants, but maybe employed and marketing together have an interaction effect between the two of them. Okay, so it could be they have standalone effects and effects together. So to account for that in the math part of the thing, we just multiply these 2 together and create a new um, column called, here I just call it marketing times employed. So it's really that simple. When we talk about making an interaction term, all we're doing is just multiplying this column times this column. Look at my equation, B2 times C2. Copy that down. We created an interaction, okay? And when we talk about adding a quadratic term, so let's say we think that the relationship isn't linear. We think it's curvilinear. All we got to do, we come in here and take, let's say we think marketing is the one that causes the curvilinear relationship. We can just take marketing and square that term. And then you can just copy this on down. But see, all we're doing, we're just taking marketing times marketing. I could have put marketing squared. I just do things the easy way. That's my way of life. But I have a hard time finding that little caret button on the keyboard. You know what I mean? So nonetheless, it's kind of a joke. But it's that simple. So everything we're talking about tonight, don't overcomplicate it. These are very simple things we're talking about, but we're using words that make it sound complicated. Okay, so tonight we're going to be talking about multiplying 2 variables together to create a new column, or just squaring a variable to create a new column. The end. Okay, that's that simple. Okay, but the words are going to make it sound complex. And I have videos. I just made them yesterday. In my defense, I was on a lot of cold medicine stuff yesterday when I recorded those. So if I seem a little out of it, that's what was going on. But they're up there. They've been up there since yesterday afternoon. And they'll walk you through how to do the the logistics of these things. Now, one thing about chapter eight, I don't know, this is a new version of the book. Like I said, the old version of the book would walk you through how to do all this in Excel. Okay. But but for some reason, for chapter eight, it's the only chapter I've seen so far. It only shows you how to do it in R. Okay. So this is more important than ever to watch my videos because the book doesn't teach you how to do it. It doesn't explicitly state how to do it in Excel. Okay, so it's not going to give you those step by steps. And I'll email the book company and tell them they need to fix that in the next edition. Maybe they'll hire me to write it out for them. Um, anyways, but I wrote the stuff out. Um, well, shoot, I hope I didn't lose it. Wouldn't that be something if I did? Nonetheless, I did write it out myself. Oh, here we go. Yeah, but it's just in handwriting. But I guess if worst comes to worst, you can you know, do that. Maybe I can sell that to the book company. What do you think? You know, they've done it before. Okay, so what we're doing, remember from last time we talked about the regression equation. Again, don't let this stuff be complicated. Okay, it looks horrible with numbers and letters and all, but y is what we're predicting. Okay, y hat means like the average of the y's equals the intercept plus whatever our beta is of our first variable plus the beta of our second variable and so forth. All right. So that's what we've looked at so far, purely linear regression. Okay, but sometimes there's a partial effect that depends on another predictor variable. So it could be that two variables together have an effect that they don't have individually. So here's just some other examples. It's commonly assumed that an additional bedroom results in the same increase in the house price regardless of the square footage. The assumption may be unrealistic because for larger houses, an additional bedroom often results in a higher increase in house prices. In other words, there's an interaction effect between number of bedrooms and the square footage of the house. Okay. So basically what they're saying is you got when you're predicting house prices, number of bedrooms and square footage are two great predictors, but also together they have an effect that way. Because who wants, like a 1,200 square foot house with 9 bedrooms? Wouldn't that be weird? You know, so those would be some tiny bedrooms. But so if the two increase and the house needs to make sense for the square footage, that would affect the price of the house. So that's why we create these interaction terms by multiplying things together. So let's see. And here again, we're making it sound confusing. Each interaction variable is a product of two interacting predictor variables. That's the truth. Product means multiply, right? So we're just taking two variables, and the example we just had, where we had marketing and something else, and we multiply them together. That's it. We just create a new column, multiply them together. And you can have three different types of these. So you remember dummy variables, we would code things 0 and 1, like you might have gender or something along those lines where 1 is male and 0 is female or something like that. So that's a dummy variable because you can't put words in there. You got to put numbers. So you can multiply two dummy variables together. That's one way of doing it. You can multiply a dummy variable and a numeric variable together. So you could have like gender times square footage, just something there. Or you can have two numeric variables like bedrooms, number of bedrooms, and square footage. So just different ways you can go about it. And the example I work in the video, I just use two numeric variables, but the process is exactly the same if you're using two dummy variables or a dummy variable and a numeric variable. You just multiply them together. Okay, so I didn't see the point in making three different videos. Excuse me. Consider a regression model with two dummy variables, D1 and D2, and an interaction variable, D1, D2. So here we see the equation is changed. So like to me, this just makes sense. But to you guys, is it just a bunch of like letters and numbers and gobbledygook? Or do y'all get it at this point? So, I don't know if you guys ever watch Young Sheldon. Any of y'all seen Young Sheldon? Just a couple of you. Okay, so I was watching one today. It's like him and this professor he's friends with. They had all these chalkboards and formulas on them and stuff like that. I don't even know if those are real formulas, but it could be anything. You know what I mean? It just looks like nothing to me and gobbledygook. But so I don't want you guys to look at this and see the same thing like in a Young Sheldon episode, okay, where it's just all these complicated looking things. It's everything we looked at last time. Okay, so here we have y is what we're trying to predict equals your intercept plus, your beta is just that number in front of your first predictor variable. Here it has a D that just means dummy. You could put an X there if you wanted to. I would put an X if I was writing it out. I don't put D's for dummies. But times dummy variable 1 plus your beta times dummy variable 2 plus your beta 3, that's just the number in front of whatever, your predictor is times D1, D2. So you know how we created that interaction term in Excel I just showed you? Well, that's all this is representing is this D1 is the same number as this, D2 is the same number as this, but we just have the two multiplied together. That's the only difference in this equation. Okay, it's got an interaction term. And you should be, at this point, able to look at this and say, that's not a third variable. That's the first variable and the second variable multiplied together. Okay, and you can look at the 3 on beta of 3 to know that this is your third, even if you didn't have the rest of the equation. And the E's always there just to remind you that there's error, like you're wrong. Like it's just a matter of how wrong are you, okay? Because everything that's ever been measured or predicted has been done so inaccurately to some degree. So here's an example data where we collect on starting salaries of business graduates. Salaries in thousands, so just keep that in your mind, along with the cumulative GPA, whether they have an MIS concentration, and whether they have a statistics minor. So we see the first one's numeric. Well, they're all numeric, but the first one's a regular variable. And then these, or continuous, I guess you would call it. And then these are dummy coded because you have ones and zeros. So here's the data we're looking at. It says estimate and interpret the effect of GPA, MIS, and statistics on salary. Predict the salary of a business graduate with and without a MIS concentration and a statistics minor. Okay, and then extend the model from part A to include the interaction between MIS and statistics. So here we know when they say include the interaction between MIS and statistics, we know in Excel, we're going to have to create a new column where this is multiplied times this, just like I did in Excel earlier. And then it says predict the salary based on, 3.5. So, and that means you're going to have to write out the equation. So here, this would be the output you get in Excel when you go through running the regression analysis. Now, Excel doesn't spit out the two models pretty next to each other like this, but when you watch the videos of me working the chapter 8 problems, you see I usually take the output of both models and cut and paste them into one sheet so I can compare the two. But here we know this is the interaction model. It says model 2, so that's one way to know. But we know because we have MIS times statistics, this one says NA and this has it in there. So here we see that, this one has the variable and this one doesn't. So this is the part B. And we see that, the asterisk means that these are significant betas. These asterisks are all significant. Now that you throw them out if they weren't, just something to notice. And then these are the p-values down here. They're all less than 0.05, so it lets you know they're significant. So, and then adjusted R-squared, we always look at that. So is the Model 2 better than Model 1? Well, it is a little bit, even with the penalty that they give it for having the additional variable. So 0.80 is greater than 0.79. So we say the interaction term does add something to the predictability of this model. So how do we estimate this stuff out? So if we're using a GPA of 3.5 with no MIS concentration and no statistics minor, we would just take the regression equation we have right here. And this, remember earlier we had the intercept, the B of 0 plus B of 1, D of 1, and so forth. Well, this is just putting numbers to that. So salary equals, now let's look at this, 44,073. These numbers are coming right off of here, okay, because this is the regression output. These are the betas. So 44,073, 6.6, 6.6, 6.7. They're the numbers that you would cut and paste into the equation. You see where those are coming from? Do you? Okay, because they're coming right out of the output from regression. So when you're writing these out, so here's the intercept. Again, I'm going to go back to that. Look at all these numbers, 6.6, 6.7. They're coming right from here, from your regression output. So you just take those and then put them in here. And then we know 3.5 is the GPA. So this is GPA. So the beta of the GPA variable times 3.5 plus the beta of whatever this one is, MIS concentration times 0 because they don't have one, right? That's where we get the 0. And then statistics is 0 because we say no statistics minor. And did we technically have to put these two in? Would the answer change? No, but we're just doing it for good form, right? Because the zeros take it all out. Um, and then, so the next one says we want to calculate a 3.5 GPA for somebody who's a MIS major and a statistics major. Okay, so here, again, going back to the output from regression, here's our intercept, and then here's the betas for everything that we're going to be putting into that equation. So here's the intercept off of that output. Here's the beta for GPA times 3.5, just like up here. But now we have ones because they're MIS concentration and a statistics minor. So then we take the beta off the output and put it times 1 plus the beta of statistics minor times 1. And here we have to put these in, right? Or it'd be off. And we see it's higher because they have these two minors. So it's really that simple. It took me longer to say this than it would take you to calculate it, because regression runs in a second, right? And the great thing about Excel doing regression, used to you couldn't do Excel or regression with Excel. You'd have to use something else like SPSS or something more sophisticated, but it was harder to get data into those software packages. But Excel's easy to put data in, and now with this Excel, with the regression, it makes it easier to analyze as well. So, so here we go. No, it looks complicated, right? It looks like the young Sheldon math, but it's not complicated at all. Okay, because really, all those numbers, just going back to this, Excel calculated all these for you. You're just literally cutting and pasting these numbers from here into this equation. Okay, and then like for instance, when you see beta of 1 times x of 1. That sounds a little confusing, right? But when you see the number times GPA, that's not confusing at all, right? Because you just put the GPA there. And when you see the number times MIS, that's going to be a 0 or 1. And same for statistics. So this is how I see it. Like when I look at that output and there's X's and D's and all these different things, I replace the X's and D's with what these variables are in my mind. Okay, then you can know exactly what everything is. Okay, so we did this one. Okay, and an interaction variable. Okay, so this is the same thing with an interaction term. So here we go. We see, we got our intercept plus our beta of 1, x of 1. We know there's a dummy variable in this one, so it's going to be a numeric times a dummy variable because that's a d, plus the interaction effects of beta 3 with x and the dummy variable. Okay, so and then finally, you can do two numeric variables. And this is the one I worked through for chapter 8. Same equation. You just have an x and an x instead of an x and a d or a d and a d. And then you have x of 1, x of 2. So personally, I don't even see the point in putting the d's in there, because the variable's a variable, but they're just illustrating that these are variables that we transformed from some kind of category into zeros and ones to let you know. I guess that you have to go back and interpret what the 0 and 1 means. No. Okay. Yeah. So here's just another example. I'm going to go through this quickly. So here's what your output would look like for an interaction term. This is the one that you remember I just had that Excel file up. And so we have our constant marketing employed and then marketing times employed. Remember we just did that at the very beginning of class. So this is kind of what the regression output would look like from that. Model 2 is the interaction one because it has a number and this one doesn't. And you use the adjusted R squared to see if model 2 is better than 1. And here model 2 is slightly better than model 1. So you would say model 2 is the better model. But you can look at this beta here and tell that it's not adding a tremendous amount, but it's adding enough to carry its weight, okay, to leave it in there. But you see how, like this is a larger beta here. And this is kind of what lets you know, see how this one's significant and that one's not. But you wouldn't throw this one out. But the reason I'm bringing this up, significance will change sometimes when you take a variable in or out of an equation. Okay, so here you look at this standalone, just marketing and employed. If they're the two things we're using to predict this variable, marketing and employed are both significant predictors, right? They got the asterisk. But when you throw a third variable in the equation, even when that variable is an interaction term created by the two original variables, now we got employed and the interaction term are significant, but now we see the marketing is no longer significant. Okay, but the overall model is significant. Um, and the R squared goes up. But it's just a funny thing with regression. When you throw in variables or take out variables, the significance or even the sign of the betas can do crazy things. I mean, it's predictable through the math, but they might switch signs or they might come in and out of being significant. So everything I walked you through earlier about how to calculate this stuff, here it's just done again with two non-dummy variables. Okay, so all the math is the same of everything we're talking about of how to get these things. So, and then one thing to look at here is when we get to the dummy variable, let's see. Yeah. You have the two, you multiply the two together. So if you have, like in this example, 80 and 50, you're multiplying 80 and 50 together and 80 and 80. So you'll see that when you go through the chapter 8 video, I'll point that out pretty good that that's what's going on there. And you'll pick this up when you're typing in the formulas in Excel and you're following along with me. You'll see the little changes. I mean, that's the way it really makes sense to me is when you're doing it in Excel and you're having to write the formulas out, you really get a good grasp of what's going on as far as this goes. Now, so that's kind of the end of our linear regression part. So up to now, we've been talking about still putting a straight line to the data, right? Linear regression. And now we're looking at, well, what if the relationship's not linear? What can we do? If it's not a straight line. And, remember earlier we talked about how it can be a positive relationship where it's going up like this, a negative relationship where it's going down like this, or no relationship where you just have a horizontal line. Okay, but they're all lines. You get it? Like either it goes down forever or it goes up forever or it has no relationship. But when we talk about curvilinear, it's either going like this, up and down, or it's going down and back up. Okay, so one additional thing to looking at curvilinear relationships, besides it just not being a straight line, there's a maximum or a minimum of that. Okay, so let me just draw a picture here, which I'm a great artist, you'll see. And my daughter is a wonderful artist. If you come by my office, you'll see she has all kinds of things. But you see this, can you see it? It's just an arch, right? There's a point here where that's the maximum, right? And if you're trying to predict sales or income or something like that, you want to know what this maximum point is, right? So we're going to look at a formula for how to calculate that because that's an important thing. That's where you want to be. And then if like you turn the same thing upside down, right? There's a minimum here, right? Somewhere right in here. And you might, if it's expenses, you might want to know exactly what is going to get us to that minimum. All right. So we're going to look at a formula on how to do that. So many times linear regression won't work if the relationship's not linear. So we can capture many interesting nonlinear relationships within the framework of the linear regression model by simply transforming a response or predictor variable. And in this chapter, we're going to look at squaring the term. So here we are back to our same old formula. Y equals, y is what we're trying to predict equals the intercept plus, our beta of the first predictor variable plus the beta of the second predictor variable. I mean, I'm sorry, this is, yeah, the beta, it's not a second, but this isn't a second predictor. It's the first predictor squared, you see? So by squaring that term, multiplying times itself, like we did at the very beginning of class in Excel, that makes the relationship nonlinear. It makes it curvilinear, where it curves, like the thing I just drew on the sheet of paper. Okay, that's all it does. Was it complicated for us to make that term? No, we just took something and multiplied it times itself. Took a second, right? It took literally like 1 second. And so that's all we're doing. It sounds complicated, squaring a term in a quadratic regression equation. But all we did, we went in Excel, created a new column, and multiplied another number by itself. That's all we're talking about here. So here you see these relationships are not a line. Okay, so here's the data points. Here's the data points graphed as a scatter plot. And in this one, we see it's a curvilinear relationship where there's a minimum value here. And then here we see it's curvilinear, meaning not a straight line, where there's a maximum value. So just think about the one that's curved like this, like a U shape. They have minimum values that we're interested in. And these that are curved like a lowercase, well, we call it inverted U is what we have to call it. They have a maximum value we're going to be interested in on top of the whole relationship itself. So would a straight line fit this data well? No. So we can just graph this stuff and look at it. You know, it's not very scientific, but it lets you know what the data looks like, and you can fit it to that better. Okay. And remember earlier I was talking about we care about that minimum and maximum number, okay? Because like we want to maximize income and minimize expenses, and if we're doing equations to do those things, that's important. Here's the formula you use to calculate what that is. Like what's the optimal number for X to maximize? Like what's the optimal amount of marketing expense to um, increase sales the most or something like that, because at some point marketing, if you spend too much, it's going to take away from your bottom line, right? Otherwise everybody would just keep spending on marketing forever, you know and just to increase their sales, but at some point the returns diminish. So to calculate these maximum minimum numbers, we put in, you can just type this out, the formula, and you have to put a negative here. Sometimes I forget to do that, but you just literally have to just hit the negative thing when you're cutting and pasting these formulas together. And I point that out very clearly in the chapter 8 videos on how to do this. But it's negative B1. So it's just this first beta with a negative sign in front of it, okay, divided by 2 times the beta of 2. So it's just this number times 2. So when you get your regression output, all you need are those 2 betas to calculate the minimum or maximum number. Now, again, the maximum, you're going to use that if it's a inverted U-shaped curve. And if it's a U-shaped curve, the minimum is going to be what it comes out. But it's the same formula for either one. Okay. So you don't have, there's not a maximum formula and a minimum formula. So here, I mean, I'm not going to go through this, but so much. Here's just the data when you're doing a curvilinear relationship. You're trying to predict wage and you're using graduate and age to predict that. Okay. And then they're going to say, predicted at 30. And then this is the thing that's kind of new. According to the model, at what age will a college graduate attain the highest wages? Okay. And that's when you use that formula. When they ask you a maximum type thing like this one or a minimum type thing. So we're going to kind of just walk through how to do that. So here, by first graphing all the data that you have, you can look at it and tell that a straight line is not going to fit this as good as a quadratic line, right? Because the data is kind of curved in the scatter plot. So that lets you know you're on the right track there. Um, and then here's your output. So a lot of times what we're going to do in this class, at least in chapter 8, we're going to run it both ways. We're going to run a regular linear regression and we're going to run a quadratic equation. And then we're going to compare the two to see which one's better. And we're going to use adjusted R squared to do that. Okay. So again, going back, we're running this linear regression line. We're running this linear regression analysis with a straight line. Then we're using this quadratic regression equation here with the curved green line. And here's just the information on those two. So the adjusted R squared, the linear one is 0.33 and the curvilinear one is 0.85. So obviously the second model way outperforms the first model. And then we can see here we're looking at age, not graduate, because age is what we squared. Okay. And we see all three of these are significant. That lets us know they're all contributing. And I mean, this is a huge difference. So we know it's fitting the data great. And then here's our equation. All we're doing is the only difference between the first equation and the second one is we have age in here twice, age and then age squared. That's all we're doing to give it that shape. The squared term is what gives it that curved shape. Isn't it funny? It's that easy. Like you would think it would be something way more difficult than this. I feel like the young Sheldon stuff, if you understood those equations, if they're real, would not be as difficult as you think. Okay, so again, you see these numbers up here. This is our intercept, our beta, 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 and these numbers are right from this output here. Okay, so 6.1, 2.0, 0.02. All right, so remember those, and there's our intercept. This is right out of the Excel output. Okay, so here you see all those numbers here again. All right, and then here's the one. Everything's the same here as far as calculating if someone's 50. For their age and so forth to get these things as what we've done before. But here's the difference calculating a maximum or minimum. So I said it's negative 2.0. So you take this beta here because we're looking at the age. Okay, that's why. So you would cut this number here and put it like in a new Excel line. And then, but you need to put a negative over it. You see, we don't just take that number, we make it negative. Okay, divided by 2 times the beta of the squared term. Okay, and then that equals the age that we're looking for here. So here they're saying the maximum age is 49.19. Okay, for maximizing income after graduating college. All right, so it's very simple. It's a simple equation. You just got to remember to put that negative sign in there. And the reason this one's negative is because this coefficient is negative. You see what I mean? So if this coefficient was negative, taking a negative to negative makes positive, right? Okay, so that would be a tricky thing too, if that was the thing. But just keep that in mind. But this one happens to be positive, so we make it negative. And that's how you calculate the maximum or minimums. Okay, I'm going to take a break there because that's the end of our kind of looking at equations. And the next, we're just going to talk about partitioning data here on out. Are there any questions or anything in the chat?
I have a question.
Yeah.
So with the negative sign, does it mean if we had instead of a positive sign attached to it and it was a negative, would it change to positive here or will still maintain negative because that's the formula? Because you are saying something that this is positive, that's how come it changed to negative. So assuming it was negative here, would it change to positive or if it's negative
Well,
throughout?
if this number here was negative, if it was minus 2.0058, and then you made that negative, this number would be positive. Okay, but see, this one is negative, so you just take whatever it happens to be. So if this one's positive, it's positive. You see what I'm saying?
So does it mean that it's not a constant formula that it has to it always has to be a negative? It's not a formula, it can change. Is that what it means?
Well, it just means you make whatever number you get from this beta, you make it negative. Like, if you multiply two negatives, you get together a positive. You can just pretend like there's a -1 you're multiplying it by in your head, if that's what you need. You know what I mean? So if you take -1 times this number, you're going to get negative
Okay,
2.0058. But if it
I
was
get
a negative 2.005 and you multiply it times the -1, it'd be positive. You see what I'm saying?
yeah, so it will be positive. That's what I'm saying. So when it's positive, does it mean that we change the formula to positive or the formula has to be negative? Like you just said, if you multiply, you're going to get a positive. So does it mean that if it was positive, we'll get 2.005 instead of negative 2.005? Or the formula says it's supposed to be negative 2.00, like it's supposed to be negative always.
No, in no way is it saying it's supposed to always be negative there.
Okay,
You might as well, in your mind, just take a -1 and multiply it times this beta.
I get it.
That's,
Thank
yeah, that's the best way to explain it. Yeah, it's just take the negative of whatever that beta happens to be there. Yeah. So any other questions? I forgot my water. I usually take a water break at this point. No. All right. Well, let's see. Not a whole lot more. Okay. So next we're just talking about cross-validating data. So up to this point, we talked about, we just have our data and we use it to create a regression equation. Well, that's not always the best thing to do because you can fit to that data and it's a great predictor of your data that you have, but you're using a sample, right, to create a model. And then if you went and used the formula that you created on another set of data, it might not fit it well at all. because you've done what we call overfitting the data, okay? Because it's made just to your data. So sometimes when we get a data set, we'll take part of it and create our equation with, part of the data, and then we'll use the data we haven't touched yet to test the equation that we've made, to see if our data is overfit. So let's see what it says overfit is. Overfitting occurs when an estimated model describes quirks of the data rather than the relationships between the variables. Okay. Yeah, so here, I just want to read this other one. It's possible a model performs well with the sample data used for estimation, but then performs miserably once a new sample is evaluated. So that's what we want to avoid sometimes, and we'll partition the data. Your model might become too complex. It fails to describe the behavior in a new sample, which is what we're worried about. And the power for a new sample is compromised. So if we get new data, it might not work as well on that. So this is way overcomplicating things here, but cross-validation is a technique that evaluates predictor models by partitioning the sample into different parts. You have a training set and a validation set. So the training set is what you use to build and train the model. So it's what you use to create your regression analysis and look at all the things we've been doing so far. And then your validation set, you would use to test that to see if it performs as well on that. And they're just saying the RMSE is a good thing to use to look at how well that performs. And it says it'll be lower for the training set than the validation set. All right, so here's one way of validating the data. There's two different ones we'll go with. The holdout method partitions the sample set into two independent, mutually exclusive data sets. So this looks like about 3/4 of this one. It doesn't have to be 75%. The book just kind of uses that as an example. It could be 60/40, 80/20, whatever makes you happy. But the point is here, we use this, one example is using 75% to create the model, like the regression equations we're making, and then 25% to test it. Okay, so here's the steps to that. You partition the sample into two parts, use a training set to estimate your competing models. Because remember, we've been doing competing models the whole time, right? We create model one without the interaction, model two with the interaction, and same with our squared terms and everything else. Then use the estimates from the training set to predict the response in the validation set, and then calculate the RMSE for each competing model. Okay. And then conflicting results are a sign of overfitting using the model. Okay. So we would like the model with the best performance in the training set to also have the best performance in validation set. Yeah. So if you got two or three models that you're running through and one does the best in your training set, you would hope that that same one does as good in the validation set. But it doesn't, then you know there's something wrong. You've created too many variables or something using variables that don't matter, and then that's throwing off your set there. Okay. So let's see. Okay, so here's an example of output if you had two models on a training set. Okay, so here we got the, you see model two performs best because it has a higher adjusted R square. And then on the model two of the validation set, we also see that that has a higher score too. So that goes along. So, but if this didn't have the higher score, we would think there's a problem there, and we need to go back and look at how the models that we created, because they may be overfitted to the data. And last, just doing it one time the way we did it isn't the only way. You can do it this way here. So the k-fold cross-validation method partitions the sample into k subsets. So k is your number of predictor variables. Okay, so if you have 4 predictor variables, that's what this one is here. Those are your x variables or d variables, or a combination of x and d variables. So you're basically partitioning it 4 times. So if this was your data from observation 1 all the way to observation, 200, 1 through 150 would be in your training set, and then the last 50 would be in your validation. But here you see how they're taking the 100 through the 150th one for validation, and this one 50 to 100 for validation, this one 0 to 25, 0 to 50 for the validation set. Y'all following? So you're doing it 4 times, basically, is what it's telling you to do. Now, this is obviously more work, but it's probably a better validation of whether you have overfitting or not, because you're using I guess, every bit of the data to validate it across the whole thing, and also to form your um, equations as well. So that's just another way of splitting it up. Same thing, just more work. So that's everything in a nutshell there that I got. Let me stop my share. All right. So what questions do you guys have? Not all at once. Okay. You tired? Because I ran a little longer than I try to be. I try to keep you guys to 30 minutes if I can. So, all right. Well,
Um, I
yeah.
do have some questions about the paper.
Yeah, well, fire away.
The next section that's due on Tuesday.
Hmm.
So when it said the current state of the analytics, I was a little confused with that heading. And then when I read the example, it looks like they're just talking about some of the issues, and then it goes into the section where we need to write about the options that are out there. I just want to make sure I was following that
Yeah,
correctly.
well, let me pull up what I say in the um in that little outlining thing I gave you so I don't contradict myself. Let's see, because I changed things a little bit between the last time I taught this class with the other version of the book and this version of the book. So sometimes if I don't pull it up, I get a little confused. Oh yeah, so this one I want to know like what specific system application, resource management system or whatever the company is using and where it came from. You know, like did they create it themselves or did they buy it or you know what is the thing they're using? You know, because are they using SAP or you know something along those lines or is it something specific? You know, when I was in the jewelry industry, we used God, I forgot what the name of it was, but it was it was software that was made just for running a jewelry store, you know,
Mhm.
and there were only two. There were only two, like at least when I was in 20 years ago in the jewelry business, every jewelry store in America used one of two different systems to, I wouldn't say everyone, like 90%. Okay. It was called ASC. That was one. There was ASC, and there was one other newcomer that was trying to come up and take their market. But um, and what ASC did, it did everything. It managed your inventory. You could have as many stores in there as you wanted in a corporate office, and it handled your point of sale and your keeping up with all your expenses and your accounting and all that stuff. So, but for that industry, ASC at the time was had a probably a 80% market share. You know of all the jewelry stores in America, you know? So what
Um,
is it for your industry?
well, I'm doing the hospital industry. I mean,
Mhm.
they have clinical decision support systems, and then they also have where some of them use Power BI now, where they're taking a lot of the clinical things and they can use them on the other end to make financial decisions and management decisions and all those kinds of things. But since I'm doing the industry, do I need to pick one of the companies and talk about what they use?
Well, what you just said is perfect.
Okay.
Yeah, just give the specific ones they're using. I mean, almost word for word what you said was exactly what we're looking for.
Okay.
Yeah.
And then the other question I had, and this is what I was a little confused about, is when it talks about the industry's current state of analytics, and then I'm just talking about the subheadings, industry's current decision support application. So I know what I just said, that's their current decision support application. But then when it says the current state of analytics, that's where I'm getting confused about what needs to go in each section.
Current state of analytics and decision support applications. So the decision support applications, that's the specific thing that we're talking about here. Okay. But what's going on with analytics overall? So the I guess the one of the bigger examples in this is just going back, dating myself a little here, is used to I mean, I'm probably one of the few people old enough to remember this, but before Walmart came around, um, using technology to stock things just wasn't that big of a thing. You know what I mean? Like, I remember I worked for a chain of, I mean, I worked at a drugstore that was part of a chain. Okay. And I would walk around once a week and I had like this little handheld, I forgot what they called it, like Palm Pilot type of a thing. And then I would have to go by everything on every shelf and like order. And I would have to touch it and say, okay, we need 5 more of this, 7 more of this, 8 more of these, and so forth, and order the whole store that way. It'd take me a few hours to go up and down all the aisles. And that was the current state of how we ordered stuff every week. Then Walmart came in and holy crap, they don't waste time doing that. The register, they got all the track of everything they're selling, and then they would just take that information and reorder off. If you sell one, order one, it'll be there next day. You know, so that's what I'm talking about at the current state of analytics. Like how its use has changed, in that example from a dude walking around with a little Palm Pilot to you're just using the information at the register and ordering it immediately. So is there
Mhm.
something like that going on in your industry? Does that make sense?
Yes. Well,
So
some
like
of
at
them are,
UWF,
there's
well,
a there's a huge need for technology to come around, but that's because like the elderly population's going up and there's more like
mm,
revenue streams and like I can come up with ways of why they need to use the clinical decision support systems. And so
mm.
um,
Yeah, so just like one thing that's changing where I work at is we're not well, for a long time we looked at people need these classes to graduate, right? There's a list of classes. If you're an accounting major, these are your classes. You take them this order. We got a carousel for you. Take this. Everybody takes this the first semester. Everybody takes this the second. Everybody takes this the third, and everybody takes this the fourth, right? Done it like that since the beginning of time. Okay. But now we got a new provost that's a math major or math PhD, and boy, I mean, I'm really impressed with this one. I can't remember what the system's called, but we got a new system we use, and it looks at each person individually and where they graduated from high school and what grades they've made in different classes up to this point. And it creates a specific order that each student needs to take the classes over the 2 years that they're an accounting major to graduate with the highest GPA and on time. So, for instance, some people can handle taking 2 hard classes in one semester and make A's on everything. And other people have to spread the hard classes out throughout the whole time. Can't do more than one at a time. But it's way more complex than that, way more complex. Um, so, and it even gives us an anticipated grade of each for each student in each class based on the order, the way they take their classes each semester. Okay, so that's the change. You see what I'm saying? Not only is the software we're using different than what we used in the past, but the function of it has changed. We can switch from one software company to another and do things the same way. But this is a revolutionary change where we're saying everybody doesn't take the same classes the first semester because that's not the best way to maximize their GPA or graduating on time. Does that make sense? So they're two separate things. You can talk about them at once, but it's a different concept.
so I see what you're saying. So you're saying, what are we using? And then some of the research I've done, like I know what we're currently using, but then you're talking about what's coming up in the future that the industry can use to move themselves forward.
Yeah, or how it's changing now. You know what I mean? Like this change I just gave you is a right now change. Like we're that's what we're in the heat of doing right now, realizing that we have the technology to get away from the everyone has the same force carousel, you
Mhm.
know? And I mean it's a little mind blowing to be honest with you, but it's useful, you know? Yeah.
Thank you.
Good question. That was kind of fun.
I just have
Anybody?
one quick question too
Yeah.
about the paper. Is the source, is the site of the softwares, I'm sorry. Is the side of the software that the industry is using valid as a source?
Well, I mean, wherever you found out what they're using would be your source. So if you find an article that says this company uses this,
Mm,
that would be your source of how they use that.
okay. Thank you.
Mhm. Now, if we can drag this out 35 more minutes, my kids will be in bed. So, just saying, make my life easier. Okay. Well, you guys feel free to text, call, or email me with anything at any time. And watch those chapter 8 videos. As I was saying, I don't know why this version of the book um, did not put that Excel stuff in there. But if you just look at my notes here, like it's not all that complicated what we're doing, and then that's why I showed you that little thing in the beginning. I tell you what, I'm going to just to hit off some problems. I am going to just give me 5 minutes, guys. Just show you a few things on the Excel. How you do? Okay, can you see my Excel now?
Yeah.
Is it the whole screen? All right, I got to move you guys down a little bit. Kenneth, you're one of the few people I can see. So if there's something in the chat, yell at me, okay? So um, the main thing you're going to be doing is running regression analysis. Okay, so you're just going to hit data, go to data analysis. We did this last time, and then go on down to regression. All right, hit OK. And then, your Y variable in the data sets that we have for this class, generally speaking, the Y variables, the first column, A1, right? So you can like click on it a special way and it'll put it all in there. But your X, these are your predictor variables. So those data ranges, generally speaking, in this chapter, you're going to do it, the variables that aren't interaction or squared first, and then you're going to run another model. So you would just take these, for the first one. And I'm not saying this is exactly how it works every time, because I know somebody will call me and give me a hard time about that. Showing you some of the clicks, okay? So that puts that there. And then you always want to click labels because you have labels, right? At the top of the data. It won't let me scroll up because I'm not in that. There we go. See, application, marketing, employed, and so forth. And shoot, I hate it when I do that. There we go. Okay. And click the confidence interval too. And I say this in the video, but I want you guys to get this. And then one person pointed out there's something that says use like the 80 observations and there's only 79, or it's just off by one. I can't remember the exact number. It's okay. Just use the data that's in the file. Don't Everything's there. It's just a misprint in the book. But anyway, so you just do these two things. I'll put it in a new worksheet. You can throw it in here. I don't care. But then hit OK. And basically, here's all the output that we were just looking at on the PowerPoints. But here, the output does look a little different. So here's your adjusted R square. I'm just going to highlight these real quick. That's important. And then these are the ones that you're going to use for your betas and your intercept for all the equations, okay? But those are really the numbers you're going to be looking at. So here and these two. And there's some other little things here and there you might look at. But for the purposes of doing these equations, that's pretty much all you got to do. Then you do it twice, okay? So let's just go back over here to sheet 1. So the second time you'll do this, you'll go to data analysis. And remember we created this earlier, regression. See all your stuff still here? All you got to do is just change this C to a D, right? And now we're capturing B, C, and D as predictors. Okay, hit OK. And then so now you got the same output, but this time it has that third variable. So I'm just going to cut and paste this and put it next to this output. This is what I was saying. I like to put the two next to each other. So here we can compare the R squares. And so you see where the data is. So you see how this R square is higher than that R square? All right. And then here's all the numbers down here we need to fill in the formulas that we're doing. Okay, so It's really that simple of a thing. So if you're doing, and then okay, there's one other thing, creating a scatter plot of stuff. So when you get to your data, you're just going to have to select whatever rows you're trying to do the scatter plot of. And then just go to insert, and then see these little dots. Yours might be a little different depending on the version. Click this and go to scatter, and see there's your dots. But the one thing about this is sometimes you want to switch the axes, like which is on the X and which is on the Y. So you'll just cut and paste these around, and then you'll just that's the easiest way I know to switch axes. I know there's some like way you can, hold on, get there. You can do that easier, but that'll switch the axes and do the graph again that way. So anyway, just little things, and I'll walk you through all that in the 2 videos. But it's that simple. Don't be overwhelmed. It shouldn't take you forever to do these things. And if you have any trouble, just let me know, okay? All right. Well, thank you all for bearing with me, and I'll see you later.